Alright, today let's have a look at the third topic in this course. We're going to have a look at the congruent triangles. Okay, first of all, let's have a look at a brief review of the concept of congruent figures. So by definition, two figures are congruent if they are exactly the same. In other words, we can slide, spin, or flip one figure so that it's exactly on top of the other figure. Any questions? Concept is pretty straightforward, right? I'll give you some examples. For example, this trapezoid is exactly the same with the one on the right, because when you flip, turn, rotate, then translate, one is exactly on top of the other, right? Note that the corresponding points are labeled with the same color here. So this point is corresponding with this point is with this point with this point here, and this point is corresponding with that point. And similarly, let's have a look at another example. These two triangles are exactly the same with each other, so they are also congruent figures, right? And here are some other examples. And note that we have some special property of congruent figures. So let's have a look at their properties first. First of all, corresponding parts of congruent triangles are congruent, which means exactly the same, or abbreviated as CPCTC. And in this course, we'll focus on studying the congruent triangles only. So for the following discussion, we'll only talk about congruent triangles, okay? For example, these two triangles are congruent. Usually we use this symbol to denote the congruent triangles. Here, a triangle DEF is congruent with triangle QPR. Usually, congruent triangles are named by listing their vertices in corresponding order, okay? So because here, D is corresponding with Q, E is corresponding with P, F is corresponding with R. Therefore, we list the three vertices in this order, okay? Usually, we'll list each of the congruent triangles in this way. And then you can see which point is congruent with the other point, right? Any questions? Again, the property is pretty straightforward, right? Congruent parts of the congruent triangles are also congruent, CPCTC. And the problem is that how can we determine if two triangles are congruent? We have a series of testing series. So let's have a look at these series. First, if two sides and the angle between them in one triangle are congruent to the corresponding parts in another triangle, then the triangles are congruent. For example, let's see the figures on the left. If we have a triangle AMN, another triangle OJB, so these little strokes here means the corresponding sides are equal, right? AN equals OB, AM equals OJ, and angle in between the two sides, angle NAM equals angle BOJ. In such a way, by the testing theorem 1, SAS means side angle side. We have triangle NAM is congruent with triangle BOJ. Okay, this is called the testing theorem 1, SAS. So the problem is, can you prove this is actually true? So are you clear with the testing theorem 1? Okay, think about this question here. Let's try to prove the theorem SAS. So given two triangles here, ABC and DEF, given AB equals DE, AC equals DF, and angle in between are also congruent, can you prove triangle ABC is actually congruent with triangle DEF? I'll give you 2 minutes to think about this question, okay? Remember, this is a theory. Theory needs proofs, right? So how can we do this? I'll give you 2 minutes to think about that, and then we'll have a look at the solution together, okay? You can compare your solution with mine. Actually, there are more than one methods you can prove this. All right, let's have a look at the solution together. So the key to prove two figures are congruent with each other is when you translate one figure to the other, each element of one figure should be exactly on top of the other figure, right? So here, okay, I'll write it here, proof. We can first put the point A on D and put the line AB on the line DE, right? This is possible, right? If you drag the point A on D and then put line AB is on line D, this is possible, right? Because we only fix one point here and put one line on top of the other one. Then next, because AB equals DE, we have point B must coincide with point E, right? Can you follow me? Because AB equals D, then B must coincide with point E. Therefore, we know the segment AB must coincide with the segment DE, right? So this proves one segment is on top of the other. And then let's have a look at the other two segments. Then because we have angle A equals angle D, then we know the line AC must coincide with the line DF, right? Because when two angles are exactly the same, they must share the same size, right? So if one of the sides AB on top is on top of D, then the other side AC must be on top of DF, which means AC coincides with DF, right? Can you follow me? And because segment AC equals DF, this is also known to us, we know point C must coincide with the point F, right? Therefore, we know the segment AC coincides with DF, right? Also, we know B is on top of E, C is on top of F. Therefore, BC, segment BC coincides with EF. And then we proved every element of triangle ABC is on top of every element on triangle DEF. Therefore, we know triangle ABC must be congruent with triangle DEF, right? Again, the conclusion seems straightforward, seems very simple, but you still need to prove this statement is true. Any statement you made in geometry, you need to prove that. Other than the fundamental axioms, okay? All right, have you finished? Okay, if you haven't finished, just give me a shout, okay? I'll wait for you for some more time. Otherwise, let's make a summary. So basically, this theorem tells us if two sides and angle between them in one triangle are congruent to the other one, to the corresponding parts in another triangle, then the triangles are congruent, which is abbreviated as SAS, side, angle, side, okay? And then we have proved this theorem like this. And well, after this class, you can think of, are there any other ways you can prove it? Okay, there are more than one way, at least, probably 10 different ways we can prove this. Okay, then let's use this testing theorem to do some exercise, okay? So in this figure below, given AB equals CD, two segments are equal, angle BAC equals angle DCA. Can you prove these two line segments are parallel? AD is parallel with DC. Again, I'll give you 1 minute to think about that, and we'll have a look at the solution together. So you need to use one of the testing theorems. to prove two lines are actually parallel with each other, right? Either the corresponding angles are equal, or alternate interior angles are equal, or the same side interior angles add up to 180 degrees. Okay, have we finished? Alright, let's have a look at the solution together. So if you want to prove AD is parallel with BC, then as I said, you need to use one of the testing theorems, right? For example, if you can prove angle ACB equals angle CAD, then we can prove these two lines are parallel with each other, because these two angles are the alternate interior angles of these two lines with a passing line here, right? So how do you prove these two angles are equal? Note that triangle ABC and triangle ADC share the same side here, and also AB equals DC, and the angle in between are also equal, right? BAC equals DCA. So basically we can prove triangle ABC is congruent with triangle CDA, right? Therefore, the corresponding parts are also congruent. Therefore, you can prove this angle equals that angle, right? So how do you write that? So to write that in a mathematical language, you need to do it like this. First of all, because AB equals CD, AC equals CA, also angle BAC equals angle DCA. We have triangle ABC is congruent with triangle CDA, right? So usually you'll put the theorem you're using to prove these two triangles are congruent. So the theorem we are using here is called SAS, right? So this is read as triangle ABC is congruent with triangle CDA by SAS. Therefore, we know the corresponding parts are also congruent. The corresponding parts are angle ACB equals angle CAD, right? Well, these two angles are alternate interior angles. Alternate interior angles are equal, indicates these two lines or two line sections. AD is parallel with section BC, right? Yes?
We know that triangle ABC is congruent to triangle CDA, so it means that they are completely the same. Can't we just say that AD is parallel to BC because we don't, because we know that they're completely the same?
Completely the same does not indicate these two lines are parallel, right? I'll set an example. For example, this is angle triangle ADC. Well, this is your okay. This is triangle ADC. This is your AD, right? And for example, this is your triangle CBA. Then this is BC here. They are exactly the same, right? So can you see these two lines are parallel with each other? Not necessarily, right? You can say they are equal, but they are not necessarily parallel. Or for another example, ADC is here. So if you move this line to this side a little bit, this is A prime and then B, then C is here. These two triangles are also congruent, and this side is not parallel with this side, right? If you move this triangle to the right by a small angle here, right? So you can only say they are equal, but they are not necessarily parallel. So be careful with the logic here. All right, let's consider another example here. Okay, point E is the midpoint of both AC and BD as shown below. Can you prove that segment AB is parallel with segment CD? Okay, let's have a look at the solution together. So again, to prove lines are parallel, you need to refer to one of the 4 testing theorems, right? Remember, we have learned 4 of them, right? So you could either prove this angle equals that angle here, right? Or angle A equals angle C, because they are interior alternating angles. Interior alternating angles indicates parallel lines. So is this true? Of course, because we know this side equals this side equals this side, and these two angles are vertical angles. Vertical angles are congruent with each other, right? So you could say because AE equals CE, also BE equals DE, angle AEB equals angle CED. Again, SAS, right? Two sides and angle in between are equal. Therefore, we can conclude triangle ABE is congruent with triangle CDE. Remember, we need to write the corresponding vertices in the same order by the theorem SAS. Two sides and angle in between are congruent, indicating two congruent triangles. Therefore, we know the corresponding parts, angle B should equal angle D here, right? Therefore, if you have proved angle B equals angle D, interior alternating angles are equal, indicates segment AB is actually parallel with segment CD, right? Alright, next let's have a look at the second testing theorem we can use to prove two triangles are actually congruent, which is called SSS. So from the name, probably you can guess the meaning of this theorem. If each side of one triangle is congruent to the corresponding side of another, then the triangles are congruent. For example, in the figure on the left, if we can have AB equals XZ, AC equals XY, BC equals ZY, then we can say triangle ABC is congruent with triangle XZY by SSS. Again, you can try to prove this theorem, okay? We're not going to talk about the proof of this theorem in this class. You can try to do that by yourself after this class. once you have proved the first one, SAS, the remaining theorems are very easy to prove. Okay, so next let's have a look at some exercise questions we can use to practice using the theorem to solve questions. So first question here in series 1, I'll give you 2 minutes and then we'll have a look at the solution together. Okay, in this figure, the size and angle have measures as shown. Can you find angle MLN? Yes, Michelle?
Do we have to prove in this question?
You only need to prove when necessary. Well, I mean, in a test, if it's a short answer question, you need to briefly write your reasoning processes. Otherwise, if it's just a multiple choice, you can just select the correct answer. Or if it's a filling in the blanks question, just give the number is okay. But if it's a short answer, you should write your solution like this. So let's have a look at solution together, okay? So we can say because LO equals MN, ON equals LM, and LN equals LN. Of course, this is the parent, right? We have, by SSS, we have triangle LNO is congruent with triangle NLM. By SSS, three pairs of sides. Since angles MLN and angle ONL are corresponding parts of these two triangles, they must be equal, right? Therefore, we have angle MLN equals angle ONL, which is 25 degrees, right? Well, you don't need to write a lot of things. Just write the key statements to lead to your final conclusion. Okay, any questions? If not, let's consider another one here. In the figure below, like a kite, AD equals CD, AB equals BC. Can you prove that DB is perpendicular with AC? Okay, let's have a look at the solution together. You can prove it like this, because first of all, AD equals CD, AB equals CB, and DB equals DB, right? So first of all, we can prove the left triangle here is congruent with the right triangle here, right? We have triangle ADB is congruent with triangle CDB by SSS, right? Therefore, the corresponding angles are equal. ADE equals angle CDE. Then we can prove this triangle here is congruent with this one, right? Because they share the same side here. So you could write because AD equals CD and DE equals DE. They share the same side, which are equal apparently. And according to this, SAS, we can prove the triangle ADE is congruent with triangle CDE, right? Therefore, triangle ADE is congruent with triangle CDE by SAS, right? So here we are using both SSS and SAS. Therefore, the corresponding parts are equal, which means angle AED equals angle CED, which is 1/2 of 180 degrees, which is 90 degrees. Therefore, we have proved section DB is perpendicular with section AC, right? Any questions? All right, if not, let's have a look at the next one. Another exercise. Can you prove that if a radius of a circle bisects or cuts in half a chord of the circle that is not a diameter, then the radius must be perpendicular to the chord? There's no diagram here, so it's better to draw the diagram by yourself. Okay, draw a circle O. Then chord AB, which is not the diameter, right? And chord AB with midpoint O here, midpoint M here, and the radius through M. Intersect with the circle at point C. And connect AO and BO. So we know this part equals this part, and AO is the radius, BO is the radius, so these two lengths are equal, right? We need to prove the radius, OC, is perpendicular to the chord AB. So we could write it like this. Well, first of all, you need to, if it's a short answer question, you need to describe how you drew the diagram, okay? So I'm not gonna write it here. So make sure you describe how you drew the diagram on the left. Then we can prove OC is perpendicular to AB. So we can say because well, let's call this point is M, because AM equals MB, AO equals BO, apparently MO equals MO. So triangle AMO is congruent with triangle BMO, right? According to SSS, 3 pairs of sides are equal, indicating 2 congruent triangles. Therefore, we know corresponding parts are equal, so angle AMO equals angle BMO, and both of them are half of the 180 degrees, which is 90 degrees, right? Therefore, we know OC is perpendicular to AB. The proof is done, right? Yes?
How can we be sure that AMA and BMA equals 90 degrees?
Because AMO plus BMO is 180 degrees, right?
Yeah. Oh, okay, yeah.
Yes.
And, okay.
So probably you want to add, because angle, add it here, and because angle AMO plus angle BMO equals 180 degrees. Therefore, okay, add it here, right? All right, then if you have no questions, let's have a look at the third testing theorem, which is called ASA angle side angle. So this theorem states that if two angles and the side between them in one triangle are congruent to the corresponding parts in another triangle, then the angles are congruent. For example, in the figure on the left, angle B equals angle E, BC equals EF, and angle C equals angle F. Then we can say triangle ABC is congruent with triangle DEF by ASA. Angle, and the side in between of the two angles. Did you get it? So if this theorem is true, immediately you should know the fourth theorem must also be true, right? Which is AAS. If two angles and a side not between them in one triangle are congruent to the corresponding parts in another triangle, then the triangles are congruent. For example, in the figure on the left, if we have angle G equals angle J, angle F equals angle K, and FH equals KI, we can also have triangle FGH is congruent with triangle KJI by AAS, angle, another angle, and side that to the opposite of one of the angles. So why this is true? Because when this angle equals that angle here, this angle equals this angle here, immediately when we know angle H to angle equal angle I, right? Then if you consider this angle, and the side in between, again, you can use ASA to prove that, right? So if ASA is true, then we know AAS must also be true, right? So we'll have a look at these two theorems together. This means you could use either ASA or AAS to prove two triangles are congruent. Okay, did you write them down? don't worry, if you haven't read them down, you can refer to my videos, which you can locate in my YouTube channel after class. You don't have to write everything down, okay? As long as you understand them, you should be fine. All right, so let's have a look at some examples. But before we proceed to the examples, you need to be careful when you're using AAS. This is a theorem which you can easily make mistakes. When using AAS, the equal size must be adjacent to the corresponding equal angles, okay? For example, the angles shown below are not congruent because the equal size are not adjacent to corresponding equal angles. Okay, if you want to use AAS, ensure that this angle, the other triangle also have the corresponding AAS here, not here. Okay. Can you follow me? All right, then let's have a look at a example. In this figure on the right, PQ is equal to PR, and angle PQY equals angle PRX. Can you prove first QY equals RX, and then XN equals YN? Okay, let's have a look at the solution together. Okay, note that angle Q equals angle R, right? And we have PQ equals PR. Then we can actually prove this triangle is congruent with this triangle here. The red one with the yellow one, right? You see that? Because they share the same angle here. And also they have some equal size, PQ equals PR. So we could write it like this, because angle PQY equals angle PRX, angle P equals angle P, this is obvious, and also PQ equals PR. Then we have triangle PQY equals triangle PRX by ASA, right? Therefore, the corresponding parts should equal. QY should equal RX. So the first one has been solved. Then consider second question. Prove XN equals YN. So we can start from the conclusion of the previous question. Triangle PQY equals triangle PRX. Therefore, we have PY equals PX. PY is here. PY is here. Px is here, right? And because PR equals PQ, this is a given information. Therefore, YR should equal XQ, right? And because angle Q equals angle R, angle XNQ equals angle YNR, we have triangle XNQ is congruent with triangle YNR, right? By AAS. Therefore, corresponding parts are also congruent, so XN equals section YN, right? Okay, have a look at the solution here. Any questions, just let me know, okay?比如话我在上课呢啊，好吧？比如话我在上课。Okay, if you have no questions, let's have a look at a summary of the congruent testing theorems. So far we have learned 4 theorems to test if two triangles are congruent, right? So they are called SSS, SAS, ASA, and AAS, right? Can you follow me? You could use either one of them to prove two congruent triangles. Also note that ASS or AAA not necessarily mean congruence. Why is that? Because if you consider these two triangles here, they have the same angle here, right? A, and they have the same size. This side equals this side equals this side, but they are not congruent with each other. Also, if you only have AAA, which means 3 pairs of equal angles, apparently you can draw 2 triangles, right? As long as each side is parallel with corresponding sides, you will have 3 pairs of internal angles. But in this case, these 2 triangles are apparently not congruent with each other. Okay, so ASS or AAA does not necessarily mean congruence. You can only use these 4: SSS, SSA, SAS, ASA, or AAS. Okay? You remember that? Okay, next, let's have a look at some related concept. First, the concept of isosceles triangles. Okay, first, if a triangle has at least 2 equal sides, then this triangle is called an isosceles triangle. In an isosceles triangle that has exactly 2 equal sides, the equal sides are called legs. So these are called leg. This is another leg. And the third side is called the base. The angle included by the legs is called the vertex angle. This is a vertex angle. And angles that have the base as one of their sides are called the base angles. So these 2 angles are called base angles. Again, these are just some common terms you should know in the isosceles triangles. Any questions? All right. So if you don't know any questions, don't have any questions. Next, let's have a look at the main properties of isosceles triangles. But they're similar triangles. What do you mean? What do you mean by similar triangles? Not all isosceles triangles are similar. We'll talk about similar triangles later, okay? In next lesson.
I mean, like, no, I don't mean isosceles triangles. I mean, like, just A, and just the caution you just
Oh,
said.
here.
Yeah.
Yes. AA means by using AA, you could prove two triangles are actually similar. We'll talk about the concept of similar in the next lesson, okay? This lesson will focus on congruence, which means exactly the same. And next lesson we'll talk about similar. Okay, next let's have a look at the main properties of isosceles triangles. First, if a triangle is an isosceles triangle, then the two base angles are equal. For example, in this diagram here, given angle triangle ABC, AB equals AC, we can actually prove that angle B equals angle C, right? Can you do this by yourself? Well, actually you can connect, let's do this together, okay? Actually you can connect point A to point P on BC, right? Such that BP equals CP. So connect A to P on BC such that BP equals CP. This is possible, right? This is doable because AB equals AC. Oh, sorry, I should not use the bar on top. Okay, because AB equals AC, AP equals AP, and BP equals CP, we have triangle ABP is congruent with triangle ACP by SSS, right? Therefore, we have angle B equals angle C, right? This is the logic behind it. So I'm not gonna talk much about it. You can try to prove this by yourself after the class, okay? And this is the first property of isosceles triangles. Next, if at least two interior angles of a triangle are equal, this triangle is an isosceles triangle. And such two interior angles are its base angles, which means given a triangle ABC, if you have angle B equals angle C, you can actually prove that AB equals AC, right? So how can we do this? Again, we can connect A to P on section BC such that AP is perpendicular to BC, right? This is also doable because by crossing a point that is outside the line, you can actually draw a perpendicular line to the given line BC, right? This is possible because angle ABP equals angle APC, angle B equals angle C, AP equals AP. We have triangle ABP is congruent with triangle ACP by AAS, right? Therefore, we know the corresponding parts AB equals AC, right? This is a proof of the second property. So here I'm not going to show you why we can draw a line AP is perpendicular to line BC. So think about this after the class, right? This is doable by only using a compass and a straight edge. Okay, if you still feel confused here, you can send me a message. Okay, this is doable by straight edge and compass construction. Okay, the third property states that if a triangle is an isosceles triangle, then the following sections coincide. First, the height on the base. Second, the bisector of the vertex angle, and third, the bisector of the base. Again, can you prove this property? Which means in the following example, given triangle ABC, AB equals AC, AB is perpendicular to BC, can you prove angle BAD equals angle CAD and BD equals CD? So again, I should not use a bar here. Okay, any ideas? I'll give you 1 minute to think about that, okay? And then we'll have a look at the solution together. Okay, let me show you the solution. You can prove. I'll write it here, okay? First of all, because AD is perpendicular to BC, we have angle ADC, ADB equals angle ADC, which is 90 degrees, right? Because AB equals AC, therefore angle B equals angle C, right? This is according to property 2, second property, right? So we have triangle ABD is congruent to triangle ACD by AAS, right? Therefore, we have angle BAD equals angle CAD, and also BD equals CD, right? Again, the concept here is pretty straightforward. Do you have any questions? Okay, if not, let's have a look at a special case. So probably you have already guessed that. A special case is that all of the interior angles are equal. A triangle is all sides equal is called equilateral triangle, or equilateral triangle is a special case of isosceles triangle. So immediately we should know that each of the interior angles is 60 degrees, right? And vice versa. If each of the interior angle is 60 degrees, this indicates that this triangle has equal sides. All of the sides are equal. Cool, can you follow me? All right, then the properties of equilateral triangles. Because a equilateral triangle is also a isosceles triangle, right? So it will have all the properties of an isosceles triangle. Moreover, each of the interior angles of equilateral triangle is 60 degrees and vice versa. Also note that we have a name for a triangle with no sides equal. A triangle with no sides equal is called a scalene triangle. Okay, then let's have a look at some examples. Okay, so far we have gone over all of the key points here. So next, let's have a look at some exercises. In the diagram on the right, AC equals CD equals DB, which are marked with the little strokes here. angle B is 23 degrees. Can you find the value of angle A? The measurement of angle A. Okay, first of all, BC equals DV, indicating triangle BCD is a isosceles triangle, right? So we could say because CD equals VD, we have angle BCD equals angle CBD, which is 23 degrees, because isosceles triangle will have the same base angles, right? So this angle here is also 23 degrees. Therefore, angle ADC equals angle BCD plus angle CBD, which gives us 46 degrees here, right? Because this is the exterior angle of these two remote interior angles. And because AC equals DC, we also have angle A just equals, this angle equals 46 degrees, right? Can you follow me? Okay, any questions? If not, let's have a look at another example. Okay, consider this question here. In the diagram O, O is the center of the circle, and section AB is parallel with section CD. So let's indicate this using these two little marks here. Angle ABO is 24 degrees, and angle OBC equals angle OCD. Can you find angle BOC? .76 is correct. Okay, let's have a look at the solution together, okay? All right, so note that OB is the radius of the circle, OC is also radius, right? So we could say because OB equals OC, so triangle OBC is an isosceles triangle, therefore we have angle OBC should equal angle OCB, right? Well, if we let angle OBC equals, well, let's say it's alpha, then this angle is also alpha, and this angle is also alpha, right? Then angle OBC equals angle OCB equals angle OCD. All of them are alpha. Therefore, we know because AB is parallel with line CD, then we have these two angles adds up to 180 degrees, right? Angle ABC plus angle DCB equals 180 degrees, right? Therefore, we know angle ABC is 24 degrees plus alpha. Angle DCB is just 2 alpha, right? Equals 180 degrees. Therefore, we know 3 alpha equals 156 degrees. Therefore, alpha is 52 degrees, right? Well, if you know alpha is here, then the angle you're looking for, angle OBC, is just 180 minus 2 alpha, right? Therefore, angle BOC equals 180 degrees minus 2 alpha, which equals 76 degrees. Can you see that? Neil, can you follow me? Any questions? Neil, do you have any questions? Neil. Okay, then let's have a look at the next one. Alright, suppose we have a diagram on the right here. AB equals BC equals AC, which means triangle ABC is an equilateral triangle. And also AE equals EB equals BF equals FC equals CD equals DA. All of the sides are equal here, such that triangle ABC is completely inside triangle DF. Can you prove DE equals EF equals DF? Well, this is a little complex. Don't feel frustrated if you can't think of that in the first glance, okay? This is the last question we're looking for here in today's lesson. Okay, have you finished? Well, actually the concept here is pretty straightforward. I'll show you why. Because if you consider this triangle here, okay, consider this triangle ADC. And this triangle here, ABE. And this triangle here, are these three triangles congruent with each other? They should congruent with each other, right? By SSS, right? Therefore, these angles are actually the same. No matter what are they should be exactly the same, right? They should equal with each other. And we also know this angle is 60 degrees, this angle is 60 degrees, this angle is 60 degrees. Therefore, we know these three angles here. This angle here equals this angle here equals this angle here, right? Both of them are just 360 degrees minus the little blue dot, two of them, minus the little blue arc, right? Which is 60 degrees. So all of the three green angles should be the same. And this side equals this side, equals this side, equals this side, equals this side, equals this side. Therefore, triangle EAD, this triangle here, is congruent with this triangle here, which is also congruent with this triangle here, right? Therefore, we have proved ED equals DF equals EF, right? You see the logic here? So please, after this class, try to write your proof in a more logical sense, okay? I have already given you the hint. So your task is to organize your language and write your proof here, okay? It's probably a little bit long, but the concept after that is pretty simple. Also, copy these last two questions on your notebook. Try to solve this together with your homework, okay? It's a straight edge compass construction problem, which is actually pretty straightforward. Well, if you can't do that after this class, I'll show you how in the next class, okay? Okay, first construct a equilateral triangle with a compass and straight edge. Can you do that? Okay, next one. Oh, this is a little bit long. Please copy that on your notebook. And you can also find today's homework in about 10 minutes, okay? I'm gonna upload that to Google Classroom. You can download it from there.